Okay, hello everyone. I welcomes to all in our lecture series on laser physics. In this lecture series, we are discussing these topics. In our last three classes, we have been discussed these three topics. In this class, we are going to discuss resonance condition and threshold condition for laser oscillation. Okay, so let us start. First, we are going to discuss the resonance condition. Then we are going to discuss the threshold condition for laser action. May you remember we have been discussed for laser action we need the stimulated emission, then we can get the laser action. So when the stimulated emission happens, the light waves constructively interfere with each other and we can get the highly coherent source or light, the so-called laser. But this will happen if the waves or light waves will follow one condition. The condition is this one: 2nl equal to m lambda. Here n is the refractive index of the medium, L is the length of the cavity. So here I represented a system or arrangement of helium neon laser. This also we discussed in our last class. So this is the experimental arrangement of helium neon laser, and this is the resonator cavity, this one. For helium neon laser, the medium is your helium and neon in a particular ratio. But in case of ruby laser, this medium is the ruby rod, that is your Al2O3 plus Cr2O3, some percentage it is added. So here medium means in which the laser action will be produced. In case of helium neon laser system, the mixture of helium and neon gas is the medium. So what will the refractive index of that gas? Here L is the length of the cavity, this one, length of the tube L. M is the integer, that is your 1 or 2 or 3. So here this condition should be satisfied for laser action. That means if we are going to expect the constructive interference between the two photons, two stimulated emitted photons, then those photons has to follow this condition. Okay, so here from this expression we can write mu. Here lambda can be written as c by mu. Mu is the frequency, corresponding frequency. So mu equal to m into c by 2n lambda. So here c is nothing but velocity of light, value is your 10 to the 8, 3 into 10 to the 8 meter per second. So this equation represents the resonance condition for laser oscillation or laser action for a particular system, right? Now we are going to go for threshold condition. This is another condition at which the laser oscillation starts in the resonator cavity. That is your threshold condition, that we are going to derive over here. What is the threshold condition? Here you can see it is well known that the intensity of outgoing beam passed through a material will be this much: I nu z. Z is the distance of travel of the light. This is the initial intensity, I mu 0, exponent of alpha mu z. Alpha is the absorption coefficient. Here you can see, suppose this is a material having thickness is z and absorption coefficient is your alpha mu. So a light, suppose initial intensity is your I mu 0 incidence and passed through this material having the thickness z. When it will be emerged from this material, some of the light will be absorbed by this material, so obviously intensity will decrease. So when it will pass through this material after traveling the distance z, the intensity will be this much: I naught, mu is the subscript, exponent of minus alpha z. So obviously this intensity is less as compared to the initial. This is the general expression we know, right? Same thing I have been written over here also, same equation number 2 here. Okay. See, in active medium, amplifying the light intensity. In general, active medium is the medium which amplifying the light intensity. So here, if I'm going to consider this laser system, helium neon laser system, the active medium or active material is your neon or mixture of active material is neon, but active medium is your helium neon mixture. So this medium amplifying the light intensity. So if I'm going to consider this equation number 2, then the light intensity is decreases the initial intensity when it will pass through a material, but whenever the light will be passed through a active material, then it will be amplified. The intensity will be amplified, means increase. So if I'm going to consider equation number 2, for amplification, alpha should be negative. Same thing it has been written. It can only be possible when alpha will be negative in the equation number 2. So if I'm going to put over here alpha is your negative, so this term will be exponent of plus alpha mu z. So in general, I have been written mod mu z. Let this is your equation number 3. So a active material have always the alpha, means absorption coefficient, will be negative value, right? In this case, the intensity of a beam after one complete passage means, suppose here the light intensity strike on the half silver and return back to the full silver plate, then reflected back and transmitted through this half silver plate. Okay, so here for one complete passage, that means from here, from this reflection, from this mirror to this mirror, length is your L. So from this point, suppose this point is A, this side is your A, this point is your A, and this is your B. So from A to B and B to A, so one complete passage for a light source or light beam will travel 2L distance, right? So after 2L distance, probabilically it will leave the active material, it will give the laser action. So for one complete passage or back and forth in resonator cavity, the intensity will be how much? This equation number 3 will be written as I mu z equal to I mu 0 exponent of, here z is your L length, again will be back to L length, 2L. So here z is your 2L. Let this is your equation number 4. Let R1 and R2 are the reflection coefficients of two mirrors. Then the intensity of a beam in one complete passage or back and forth in the resonator cavity will be reduced by the factor R1 into R2. Here gamma is a constant. Here we consider gamma is a constant, and R1 into R2 will be equal to exponent of minus 2 gamma. Okay, due to the reflection coefficient, the light intensity, reflection coefficient of mirror, the light intensity will be reduced at the time of each reflection. So when the light is struck on this mirror, suppose this mirror have reflection coefficient R1 and this here for this one is R2. So each reflection, for here it will somewhat intensity will be reduced, and here when it will be reflected from here R2, from this mirror R2 is the reflection coefficient, again it will reduce some intensity. So what will the reduced factor? Reduced factor is your R1 into R2, and it is represented in the exponential function as exponent to the power minus 2 gamma. Let this is your equation number 5. And here obviously gamma will be how much? Here if I am going to take log both the side, then we can find gamma equal to 1 by 2 ln R1 into R2. Now the resultant intensity in one complete passage will be how much? Just we have to add both the equations here, equation number 4 and equation number 5. the intensity, resultant intensity will be I mu naught exponent to the power this one 2 alpha mu mod L, this one minus 2 gamma, right? That implies I mu z, or the resultant intensity will be I mu 0 exponent to the power. Here I taken 2 common from these two terms, and we can write this one, right? For sustained laser action or for continuous laser action, this exponential factor should be 1, should be positive. Okay, so here 1 can be written as exponent to the power 0. So this value should be greater than that of the exponent to the power 0, or we can write this value 2 into alpha mod L minus gamma greater than equal to 0 should be, right? Right. That implies this value alpha L should be greater than equal to gamma. Okay, this is the threshold condition at which laser oscillation will start. Okay, this is the threshold condition. Threshold condition is your what observation coefficient into length of the tube equal to gamma. What is the gamma value? Gamma value is nothing but this one minus half ln r1 into r2 here. So this is one of the important relation or threshold condition you have to remember for numerical in your exam. Okay, so what is the condition? Observation coefficient into magnitude of the observation coefficient. Magnitude of observation coefficient, length of the tube should be equal minus 1 by 2 ln reflection coefficient multiplication of reflection coefficient of the two mirrors. Okay, here I written alpha mu is the observation coefficient of the material, active material. You just write active material. L is the length of the cavity. R1 and R2 are the reflection coefficients of two mirrors. Okay, so here we discussed what is the resonance condition, this one, and what is the threshold condition. This derivation often you can found 3 mark in your exam. Practice, remember, prepare for your exam, right? Based upon this formula, this one resonance condition, now we are going to solve a numerical which is asked NET 2023, right? Here is the question. A gas laser cavity has been designed to operate at lambda equal to 0.5 micrometer with a cavity length equal to how much? 1 meter. With this setup, the frequency is found to be larger than the desired frequency by 100 Hz. The change in effective length of the cavity required to return the laser is what? Okay. So these are the options. So this D option will be correct. How it is? Here you can see. We know for the laser action or for the laser mode, what is the resonance condition is this one. Resonance condition is this one, or you just remember this one 2nl equal to m lambda. Same thing I have been written over there 2nl equal to m lambda. Lambda can be written as c by mu, and here n is the refractive index of the material is your 1. Refractive index of the material is your 1. L is the length of the cavity and m is the integer. That will be 1, 2, 3 and so on, right? Here in this question, I forgot to write refractive index given as 1. Okay, for this gas laser, refractive index given as 1. So if I am going to substitute value n equal to 1, so our condition, resonance condition will be this one 2L equal to m c by mu or 2L equal to m lambda. Now you just check with this formula what will the figure in our mind. So if I'm going to consider m equal to 1 here, if I'm going to consider m equal to 1, then L equal to what? Lambda by 2. So L equal lambda by 2, that means this one, this whole length will be lambda by 2. So this will be the wavelength of the laser. Okay, so if I'm going to consider m equal to 2, m equal to 2, then 2l equal to 2 lambda. That means 2l equal to 2 lambda or l equal to lambda. L equal to lambda means this length is nothing but wavelength of the laser. That means this one. This standing wave we can found for m equal to 2, and this standing wave, this one we can get for m equal to 1. So this is the picture we can imagine for this question when n equal to refractive index equal to 1. Okay, so here from this equation we can found mu equal to m c by 2l. Take the derivative both the side, just differentiate. It will be del mu equal to here minus m, here 1 by l. If I'm going to differentiate, it will be minus 1 by l square del l, right? That implies del mu equal to minus m. Here in equation number 1, mu equal to m c by 2l. So c by 2l will be mu by m. So here c by 2l can be substituted by mu by m. Okay, another extra l written over here, del l, right? Here m got cancelled, and we can found del l equal to minus, here del l equal to minus l by mu into del mu. So mu is nothing but c by lambda, so it will be written as minus lambda l by c into del mu. Here in the question it has been given that the length of the resonator cavity is your 1 meter. So this length value is your 1 meter. Lambda value is written as 0.5 micrometer, 0.5 in 10 to the minus 6. Del mu is nothing but change of frequency. Here you can see what is the question. With this setup, the frequency is found to be larger than the desired frequency, around 100 hertz. So we desired suppose frequency mu, but we are getting with this setup mu plus 100. That means what is the extra term? Extra, that means this is the mu dash. So mu dash minus mu, that is your del mu equal to 100. So change of del mu, change of frequency is 100. So 100 here I have been substituted. So del L will be this one. That means length we have to reduce this much. Okay, the change in length, the change in effective length of the cavity is required to return the laser. So this extra frequency to be adjusted, what we have to change the length, we have to reduce the length of this much value, this much meter. Okay, I forgot this much meter. That means if I calculate this one, I can found 0.166 10 to the minus 12. So this will be the answer. In the answer it has been 0.167. so here 166. Okay, no problem, the answer will be D, right? Okay, here I'm going to stop this class. Next class we are going to discuss differentiation between spontaneous emission and stimulated emission, question upon divergence of laser and application of laser. Okay, thank you so much for watching this video. Thank you.